So the first thing that you have to do to find a horizontal asymptote, right, is we're looking at a limit as x approaches infinity before we even worry about the highest degree and all that nonsense, right? Then we'll worry about the highest degree. So horizontal asymptote comes from looking at the limit as x approaches infinity. Now, somebody said, look at the highest degree. That's right, look at the highest degree. Well, what's the highest degree of this function?
1 considering, I mean, it really is 2, but it's square rooted, so.
Right, so we got a little bit of a weird thing going on here is we got the squared, but we've also got the square root. So we know that we can't just directly square root 9x squared plus 2 and say that's a degree of 1, but really it is effectively a degree of 1. And let's think about this limit. This limit is approaching infinity. And as we go towards infinity, what happens to the x squared and the x? They should be getting very, very big. True? One would think the 4x and the 9x squared would be getting very, very, very large as x goes towards infinity, right?
Yeah.
Like, let's suppose x was 1,000,000, right? Well, 1,000,000 squared times 9 is huge. Is this plus 2 going to mean a whole lot after I plugged in 1,000,000 for x?
Not really.
No, not really. What about this plus 3? Is it going to mean a lot after I plugged in 1,000,000 for x?
Not really.
Yeah, not so much. And 1,000,000 is not even that big a number, right? I mean, think about plugging in, a 1 followed by 1,000,000 zeros. Well, that's still not that big a number either. And that plus 2 and that plus 3 become even more insignificant. So what we're going to do is we're just going to make a little leap here and say as x approaches infinity, these are insignificant because they become so tiny that they don't even hardly matter. And so we're going to say that this limit should be equal to the limit as x approaches infinity of root 9x squared over 4x. We're just going to get rid of them. And that's perfectly fine because that's essentially what we were doing when we were dividing by the highest degrees anyway, right? When we divided by the highest degrees, all of those things got very, very close to 0. Well, they're still getting very, very insignificant. So now we need to simplify down this root 9x squared. So how do we simplify root 9x squared?
3x.
Almost.
Plus or minus.
What was that?
Plus or minus 3x.
Okay, close, almost. The plus or minus 3x, 3x, right? The plus or minus is an important piece to this. Let me ask you this question. Suppose x is equal to 5. All right, just suppose that. What's the square root of x squared equal to? Well, it's the square root of 25, which is
5.
5. That's great. Suppose that x is equal to negative 5. Well, what's the square root of x squared equal to? It's equal to the square root of 25, which is 5. So what is the square root of x squared equal to?
The absolute value of x.
Yeah, we want to call the square root of x squared equal to the absolute value of x, right? It's a very important thing. Square root of x squared is the absolute value of x. So what should we write as the square root of 9x squared? That ought to be the absolute value of 3x. And that'll take into account the plus or the minus that, I'm not sure who that was, but the plus or the minus that somebody said about that. Everybody good with that?
Yep.
All right, cool. So now, what is the sign of 3x? If x is approaching infinity, 3x is positive, isn't it? True? If x is approaching infinity, 3x is positive?
Yes.
And when you take the absolute value of something that's positive, it just comes out to be what it already was, right? cancel the x's, and you get 3/4. This should have a horizontal asymptote of 3/4. Everybody agree with that? Y equals 3/4.
Yes.
All right, now there's a problem. And we're gonna look and see what that problem is. Right now, we had, what did we have? We had the square root of 9x squared plus 2 or plus 3. It doesn't really matter.
2.
Plus 2. And divided by 4x plus 3, is that right? Okay.
Yeah.
So we ended up getting 3/4 as our asymptote, our horizontal asymptote. Well, yeah, it sure looks like it, right? Let me plug in y equals 3/4. Right, y equals 3/4, 0.75. Sure looks like this function is approaching that asymptote as I go towards infinity, right? Yeah, sure looks like it's approaching that horizontal line.
Yeah.
Yeah. Well, what about on this side? Does it look like it's approaching that?
No.
Not really, no. What does it look like it might be approaching?
Negative 3/4.
Yeah, negative 3/4, right? If I put that in, oh yeah, that sure looks like it's approaching negative 3/4 now, isn't it? It's getting very, very close as we extend out there and get larger. So how do we account for that?
You have to find the limit of negative infinity as well.
Yeah, so we didn't do that on any of these other ones, and I'll explain why in a second. But whenever you're looking for horizontal asymptotes, you have to also look for a limit as x approaches negative infinity, because some functions have different horizontal asymptotes in the different directions. So this one is y equals 3/4 to the right, whereas this one ends up being y equals negative 3/4 to the left. And we can go through the same process saying this plus 2 and plus 3 are insignificant. And as we look at our limit now as x approaches negative infinity, to make it an absolute value of 3x over 4x. Now, what can you tell me about the sign of the thing inside the absolute value if x is approaching negative infinity?
It's negative.
Should be negative. And so when you take the absolute value of something that's negative, you take the opposite of it. And now we'll just cancel out those x's. And the limit of a constant is just the constant. So we get y equals negative 3/4 to the left. Good or no?
Good.
All right. Now, how come back here with all of these rational function ones, we didn't have to bother with the negative infinity? Should we have? We probably should have. But for each of these, we ended up just getting constants at the end. And so those constants ended up, no matter what, being positive because we didn't have any of these absolute value things in there that could have flipped the signs. So they always would have ended up being the same to the left and to the right. And we'll note that anytime you have a rational function, if it has a horizontal asymptote, it has it in both directions. But this is not a rational function. Therefore, we have to look for sure to the right hand.
Oh wait, sorry, but since it's x squared and then since it's an absolute value, how does x going to negative infinity equal to negative? Oh wait, oh, okay, never mind. Actually,
This thing inside of here, if the x values are negative.
yeah, it applies to 4. The negative applies to 4x. All right.
No, the negative gets attached to the 3x because it's about the definition of absolute value. The absolute value of x is the opposite of x if x is less than 0, right? And x is less than 0. So the absolute value of this thing has to be the opposite of opposite of 3x. Now, you're right in saying that if I plug in a negative infinity, this becomes a positive number and the denominator becomes a negative.
But then, oh wait. Oh, never mind.
Okay. Everybody good with that or no?
Good.
Okay. Cool. All right. Should we do another one like that, or we feel okay about that?
I would love to do another one.
All right, let's add a page in here. I'll just make one up on the spot here. Let's find the horizontal asymptotes of the function y equals, how about 9x minus 1 over the square root of 4x squared plus 5. Everybody good with that? So, as x goes towards infinity, that should be our horizontal asymptote to the right. And I'll write the whole thing out first, 9x minus 1 over root 4x squared plus 5. What pieces of that become very insignificant?
-1 and positive 5 root square.
Right. Yeah, then the -1 and then that 5 become insignificant as x gets very, very large. So we can rewrite this as a limit as x approaches infinity of 9x over root 4x squared, which is the limit as x approaches infinity of 9x over the absolute value of 2x. And as x goes towards infinity, the thing inside the absolute value is positive, so it's going to stay the same when we take its absolute value, cancel the x's, and you get 9/2. Good or no?
Yes.
All right. And the limit as x approaches negative infinity of 9x minus 1 over root 4x squared plus 5 should be the same as the limit as x approaches negative infinity of 9x over absolute value of 2x again, right? I'm just going to skip this intermediary step there. And now, because the x values are negative, the thing inside the absolute value is negative, which means that when I take its absolute value, I take the opposite of 2x, right? And then this is why we get a different value for this one. Good or no?
Good.
Cool. Any questions or issues with that? No? Everyone's good? What? Question?
I said no.
All right. All right, we're going to move on. We're going to look at some other limits that involve infinities. So we're going to do some of it with exponential functions. You should, I hope, be familiar with the function e to the x.
Yes.
Right? Everybody should know. I'm just gonna graph it here for you real quick. But e to the x, right? Yep. It's got a horizontal asymptote to the left of y equals 0, but to the right it does not have a horizontal asymptote, right? It increases exponentially. Right? Just real quickly, how does throwing a negative sign in front of that x affect it? What's that going to do? I had e to the negative x. What does that do?
I think it's going to reflect over the y-axis.
That's exactly what it'll do. Yep. And so we would note that that one has a horizontal asymptote to the right of y equals 0, but to the left, it does not have a horizontal asymptote. So some functions have horizontal asymptotes in only one direction, right? They don't even have one in the other direction. So good to have that knowledge of e to the x and e to the negative x. And that should help us to answer these 4 questions real quickly. As x goes towards infinity, what's e to the x? What is its value? As x goes towards infinity, what should e to the x be? It's going up and up and up and up and up, right?
Infinity.
Yeah.
Yeah, we can call that infinity, right? Technically, it doesn't exist. We'll call it. But what about as x is negative infinity? What does that one be?
0.
That one's 0. And we can think about this. I mean, we can think about just plugging in a very large number to each of these, right? If I plug in a very large positive number, well, I have e to the power of a very large positive number. That's going to get huge. And here, if I have e to the negative large number, right? Well, what does the negative in the exponent do? That negative should drop that into the denominator. So it becomes 1 over e to a very large number. And 1 divided by a large number is very. So what about for this one? What about the limit?
0.
Infinity of e to the negative x ought to be 0. That's our horizontal asymptote to the right of the one we looked at on the graph. And then the last one, x negative infinity of e to the negative x. That one should be
Infinity.
infinity. Okay, so we're going to want to know these 4 limits. And then we're going to use them and apply them to some slightly more difficult ones. Any questions on how we got any of those 4 before we move on and do some more stuff with it? No? Sounds good? All right. Let's take a look at the limit as x approaches infinity of e to the 6 minus 2x minus 5x squared. What should we do with that?
Can we just look mainly at the highest degree, because that's going to have the most impact as we approach infinity?
That's exactly what we're going to do. So we're going to take a look. We're going to look at this whole thing, but we're really only going to be concerned about just this piece of it. And so what we're going to do is we're going to get rid of that whole thing. We're just going to get rid of it and say, let's let u equal 6 minus 2x minus 5x squared, because then it's going to turn into e to the u, right? And e to the u, or e to the x, or e to the whatever variable, is a function that we know what it looks like and how to deal with it. So as as x approaches infinity, what you were saying is very important. We only really care about this largest power, right? Because as x goes towards infinity, the 6 and the power of 1 become insignificant, and all that really matters, all that what dominates this function is the largest power part of it. And so if x is approaching infinity, what is u approaching?
Negative infinity?
Should be negative infinity, right? Because we have a -5 as our coefficient on the x squared. We square the positive infinity, they still get a positive infinity, and multiply it by that negative. So we should be able to rewrite this then as the limit as u approaches negative infinity of e to the u. And just based on what we did on that last page, we should know that that is equal to
0.
Should be 0. Exactly. And if we wanted to, 6 minus 2x minus 5x, oh, that's not in there. 6 minus 2x minus 5x squared, right? And we could see that Yeah, as we go towards infinity, it sure looks like very quickly it's approaching 0 and staying right there by that 0, isn't it? Sure looks like it to me.
Yes.
All right. Now, I don't think I have it there. What about, let's just for fun, do the limit as x approaches negative infinity of e to the 6 minus 2x minus 5x squared. We could do the same substitution, right? Let u equal 6 minus 2x minus 5x squared. And if we do that, as x approaches negative infinity, what is u approaching?
Positive infinity.
Are you sure? Take your negative infinity and square it, what do you get?
Oh, it's still gonna be negative, yeah.
So that becomes a positive, but then you multiply by the negative 5, still approaching negative infinity. So this just becomes also a limit as x, or not x, sorry, u approaches negative infinity of e to the u, which is still 0. And if we look back at the graph, we can see that as we go towards negative infinity, that's exactly what it's doing. It is also approaching 0. Good or no?
Good.
All right. So let's take a look at this one. What do you think we should do?
Complete side note, I don't know if you know this, but you're not recording.
I'm not. I thought I was.
I don't
Is
see
for
the
me.
little recording thing.
I see it.
Yeah. No, it
I
says I'm
see
gone.
it.
Yeah, it
My
says I'm
bad.
recording. I appreciate it though. If you it looks like I'm not again, let me know. Sometimes I pause for some reason because I'm like, yelling at my child. Feel like I shouldn't record that and then I forget to restart it. So yeah, I definitely am though, because it says it's going. All right, so what are we gonna do with this?
Look mainly at the x to the 4th.
Okay, so yeah, and we're gonna get rid of all of that, and then that x to the 4th is the part that dominates it. So if I let u equal x to the 4th minus 2x plus 1, as x goes to negative infinity, u is gonna go to what?
Infinity.
U is gonna be approaching positive infinity. Negative infinity to the 4th power becomes positive. So this just becomes a limit as u approaches infinity of e to the u, which is
Infinity.
infinity. Everybody good there or no?
So again, on the AP test, if we were given this limit, they would have either infinity or does not exist.
Correct. Yeah, one of those. If it was multiple choice, not both of them, one of them would be there. And if it was free response, they'd accept either one.
Okay.
Yeah. All right. Let's do one more of these. Maybe, I think I got one more of these. That's the last one. What should we do? Let u equal
2x plus 3. All right. Yeah, 2 equals x cubed. I meant
x goes to negative infinity, u goes to
negative infinity.
negative infinity also. So this becomes the limit as u approaches negative infinity.
0.
Good or no?
Good.
I'll do one more that's a little bit different because this one's not a limit approaching infinity. So we got the limit as x approaches 0 from the right of e to the 1 over x. But we can use the same process. Let's just substitute out this 1 over x so that it doesn't look like a function we're not as familiar with. Let's just make it look like e to the u. Right, let's just let u equal 1 over x. And if u equals 1 over x, as x approaches 0 from the right-hand side, what's happening to this 1 over x is the x values get very small, like 0.0000000.
Goes to infinity.
It's going to go to infinity, and it's going to go to positive infinity because we are approaching 0 from the right-hand side, which means that all of these values are positive, and 1 divided by a positive has to give us positive infinity. If I was approaching 0 from the left-hand side, we're not, but if I was, I'd have negative 0.0000001, which would make this u value negative. Everybody good with that?
Yeah.
Okay. So then this just becomes the limit as u approaches infinity of e to the u, which is
Infinity.
And if I had done 0 from the left-hand side, then what should we have gotten? If we let u equal 1 over x, and x is approaching 0 from the left, then u is approaching, what did we say? That should be approaching negative infinity. So this would become the limit as u approaches negative infinity of e to the u, which would give us
0.
0. Everybody good or no?
Good.
Cool. All right. Oh, how about these ones? Those ones seem just as easy, right?
For sure.
Not quite. Let's see what happens if we plug in infinity. And what happens if we plug in infinity? E to the 10x becomes what?
Infinity.
Infinity, and then minus 4e to the 6x is infinity, right? So infinity minus.
Shouldn't we just take negative 9e to the power negative 15x into consideration, considering they're both like the biggest number? They both outclass each number in terms of being big.
Well, let's first take a look and see what happens to these terms, to get an idea of what's going on before we worry about that. Because normally they're not, we don't have, when we were talking about the other ones, squared, third, right? But raising to the power of 10x and 6x is very similar in how big that gets and how quickly it gets big. So let's just see what happens to all of them. So the first three are infinities, right? Infinity minus infinity plus an infinity. What about this one?
0.
That one's 0. And what about the last one? Minus 0.
Oh, well, never mind what I said. Yeah.
Everybody good with those last terms being 0?
Yep.
Okay, cool. So we have a problem here in that if I had infinity plus another infinity, that's still a very large number. But infinity minus infinity, anywhere within there, this is a form that is indeterminate. And I probably should have talked about this when we were doing these other ones way back when, not these ones, further back. Like when we were doing these rational functions, when we were looking for these limits as x approached infinity. Sorry, I'm going to go back there for just a second. If you just plug in the infinity, you end up with infinity over infinity. True? Way back when we did those like last week. And same with this one today, it was infinity over infinity. Well, infinity over infinity is also indeterminate. So we had 0 over 0, we had infinity over infinity, which is indeterminate, and we also have this other one, which is infinity minus infinity, which is also an indeterminate form. So anytime you have infinity minus infinity, you have to find a way to deal with it. Unfortunately, infinity minus infinity is not just 0, because there are a lot of different degrees of infinity. Some infinities are larger than other infinities, which we're not going to get into now. But because of that, infinity minus infinity doesn't necessarily just equal 0. So we're going to have to find a way to deal with this to get rid of the infinity minus infinity. Any ideas? No ideas? What pieces of this are not a problem?
The zeros.
The zeros for sure are not a problem, right? Anything that had a negative exponent is definitely not going to be a problem. So is there a way we could maybe turn all of the exponents into negative exponents, except maybe one of them?
I think multiplying it by
All right. Let's take a look at, well, that's not going to help. You guys got to find a way to do this. I was gonna write another problem out that I thought might help you, but it won't help you. So
Could you just rewrite it as, like, let's say you take e to the 10x and rewrite it as 1 over e to the negative 10x?
well, if I were to do that and I plug in infinity, what do I still get? I still get an infinity, don't I? Think you still get an infinity if you do that? All right, I'm gonna try and help you here then. Let's say you have this. How do I simplify this? How can I rewrite this?
Factor out the x squared.
Take out an x squared, right? What does that do if I take out the x squared? It drops this one's power down, right? To an x squared. And it drops this one down to a 1. True? So factoring stuff out always drops down the powers. So maybe I can find something to factor out to drop down some of these non-negative powers into negative powers. Because if they were negative powers, wouldn't that be just great? Because then those parts of it would be 0, wouldn't they? So what can I factor out of all of this? How about I factor out e to the 10x? If I factor out e to the 10x from everything in here, from all of these 5 terms, what should I get? What do I get if I take e to the 10x out of e to the 10x?
1.
Okay. What if I take e to the 10x out of negative 4 e to the 6x? I'm still going to have a minus 4 e to
negative 4 to e of negative 4x.
because these powers, 10x plus negative 4x, would have to come out to be that 6x. So what's the next one going to be? Plus 3e to the negative 9x and plus 2e to the negative 12x. And I've run out of room here, but minus 9e to the negative 25x. Do you guys all agree with that?
Yes.
Okay. And now if I plug in an infinity, what's e to the 10x?
Infinity.
Just the infinity, right? And then the 1, if x goes towards infinity, what's 1?
1.
1, right? And then all these ones with negative exponents become zeros, minus 0, plus 0, plus 0. And what do we end up with as our answer?
Infinity.
We end up. So every once in a while, you'll see one like this on the and you got to factor out that going to infinity, factor out that largest. What do you think we should do if we're going towards negative?
Plug it in.
Okay, if we plug it in, what do we get to start with?
0 minus 0 plus 0 plus infinity plus infinity minus infinity.
All right, and we've got infinity minus infinity, which is a problem. So what will we do?
Factor out the 9e to the negative 15x.
Yeah, we'll take out this, and we don't have to take out the full negative 9, because taking out the negative 9 complicates all these other constants. So we can just take out the e to the negative 15x. And if I take out e to the negative 15x from e to the 10x, that ought to become e to the 25x. And then minus 4e to the 21x. And then plus 3e to the, what does that one become? 16x. I can do arithmetic. Plus 2e to the 13x. And then minus 9. And as x goes towards negative infinity, what is e to the negative 15x?
Infinity.
So we got infinity times, and then all of these ones inside of here, except for the constant, are 0 now. And we end up with negative 9 times infinity, which is negative infinity. Good or no?
Good.
All right. Let's move on to a slightly different one. The limit is x approaches infinity of the natural log of 4x squared plus 5x minus 2. Any thoughts?
Just do 4x squared because it's the biggest, it's easily the biggest degree. It easily has the most impact out of all of them, basically.
Right. So,
well, for the positive infinity at least.
Yeah. So let's, since we got a natural log around all of this, it's gonna, I think it's going to make it easier if we substitute out everything that's inside that natural log, because we probably don't know what this function does, right, as x goes towards infinity. But we do know what the natural log function by itself is, right? If we want to think about that, what does the natural log function look like? Well, as x goes towards infinity, what's it doing? It's going up towards very slowly, but going up towards
Infinity.
infinity, right? It increases forever. It does it very, very, very slowly, but it increases forever. And what about as we approach 0 from the right-hand side? It goes down towards
Negative infinity.
negative infinity. So we want to kind of know those things. And then if we can substitute out whatever is inside the natural log as a u, we can just use that information to help us. So if u equals 4x squared plus 5x minus 2, and x goes towards infinity, where is u going?
Infinity. Positive.
Yep. Which just gives us a limit as u approaches infinity of natural log u. And we just said as a natural log function, if you plug in large numbers to it, it goes towards infinity. And what about this one down here? do the same substitution. U is equal to 4x squared plus 5x minus 2. And as x goes towards negative infinity, what is u going towards?
0.
Are you sure?
Negative infinity.
Negative infinity.
Are you sure? What is u going towards?
Infinity.
It should be positive infinity, right? Because I'm squaring that negative infinity, and that becomes very, very large. This piece dominates it. The rest of it becomes insignificant, right? And so it should go towards positive infinity. So we end up with a limit as u approaches infinity of natural log u, which once again is infinity. Any questions or issues with that? All right, let's do another one. The limit as x approaches negative infinity of the natural log of 1 over x to the 4th minus 8x. Let's get rid of everything inside that natural log. U equals 1 over x to the 4th minus 8x. And as x goes to negative infinity, we got to figure out what u is approaching. So if x is going to negative infinity, what part of the denominator is dominating the other part? The x to the 4th, right? So if I take negative infinity and raise it to the 4th power, what do I get?
A very large positive number.
A very large positive number in the denominator. So this becomes u is 1 over a very large positive. And if I'm 1 divided by a large positive, what is that the same as? Approaching
0.
0. And from which direction is it approaching 0?
The left.
We've got a positive number divided by a very large positive number, right? So what can you tell me about this fraction? It is always
Decreasing?
well, no, it's not actually. It's getting smaller, but it's always, no matter how large this number gets, it's always a positive divided by a positive, which means it's always going to be
Positive.
which means I'm not approaching 0 from the left. I have to be approaching 0 from the right because this fraction is always positive. So this becomes a limit as u approaches 0 from the right of the natural log of u. And we just looked at the graph a minute ago. What happens to the natural log function as you approach 0 from the right? It goes towards
Negative infinity.
goes towards negative infinity. Good or no?
Good.
All right. Spectacular. Any questions on anything we've done today?
Do we have a quiz tomorrow?
No, we will not have a quiz tomorrow.
Okay.
Yeah, we'll have a quiz. We'll probably just have one again this week since we got the Wednesday off. It'll probably just be on Friday because, yeah, we'll have a quiz on Friday for sure.
All right. Thank you.
Yep. Okay, let's see. Should we continue? We should probably just continue, huh? Should we just continue? Move on? Why not? All right, we still got a couple minutes. So we're going to talk now. We're going to sort of move slightly away from limits, although we're still going to be doing limits. we're going to talk about what it means for a function to be continuous at a specific point. And I think we've already talked a little bit about this maybe, but for a function to be continuous at a specific point, we know that it has to not have any breaks or holes or asymptotes there, right? I mean, that's, if it's continuous, it's continuous. It doesn't have, breaks. It doesn't go up to asymptotes, right? It doesn't do any of those things. If it's continuous, it's just continuous, right? You can draw it without picking up your pencil. So one of the things that calculus is a little bit concerned with is a function continuous at a specific point? And so we say that a function is continuous at a point if these three conditions are satisfied. The first condition being the function itself is defined at that point, right? So if the function is not defined at the point, you clearly can't be continuous, right? If I have a place where my function is not defined, even though it's continuous all the way up to it and continuous all the way after it, I'm not defined at this point, I can't be continuous. True? Do you all agree with that?
Yes.
That it can be continuous at that point. Okay, good. All right. The second criteria is that the limit has to exist. So let's suppose I'm looking at the limit at this value. Well, we're using C, so we'll use C here. And my function does this. Okay. Does the limit as we approach C exist?
No.
No, because from the left, it's whatever this value is. And from the right, it's whatever this value is. And they're not the same. True? And if the limit from the left and the limit from the right are not the same, well then, it's not continuous. Okay? That limit doesn't exist. Even though the first criteria is met, right? The function is defined at C, but the limit doesn't exist there. So we have to have the function is defined and the limit must exist at that point. And then lastly, those two things have to be the same. Okay? The limit as we approach that value of C of the function has to equal f of C. Okay? So these are the three criteria for a function to be continuous at a point. And if a function satisfies all three of these criteria for every point on that function, we say that that function is continuous for all real numbers. Okay? So how many different types of discontinuities are there? How many different things make a function not continuous at a point? How many different ways? Anybody have an idea?
I believe around 5.
Nah, less than that. Just three types of discontinuities. And they're called removable discontinuities, of which there are sort of two different kinds. Then we have jump discontinuities, and we have what's called infinite discontinuities. So a removable discontinuity is just what it sounds like. You've removed one point from it. Okay? So it's continuous everywhere else perhaps, but you've removed that one point. And a removable discontinuity could also have that point filled in elsewhere, right? At the same C value might have a different Y value than what we have everywhere else. That's still called a removable discontinuity. Then we have what's called a jump discontinuity, which is what I drew on the other page, right? A jump discontinuity is it stops, there's a point there, and then it jumps to some other open circle and has some more of the function after that. And then there's also an infinite discontinuity, and that's anytime it's approaching an asymptote. So you're going to want to remember these three names: removable, jump, and infinite, because sometimes they will ask you to classify discontinuities on graphs, and they will want you to specifically use those three names. Good or no?
Good.
All right. So real quickly, let's think about our definition of continuity. The first criteria was the function has to be defined, right? So for this first removable discontinuity, does it meet the first criteria? Is f of c defined?
No.
No. So this one already, we know it doesn't meet number one. It fails number one. What about this one? Is f of c defined?
Yes.
Yeah. What about criteria 2? Does the limit as x approaches c exist? coming from both sides. Yeah, I'm approaching the same number. That limit exists. Okay. But what about number 3? Does the limit equal the value of the function?
No.
No. So this one fails number 3. That was the worst number sign. Or whatever. Hashtag. That's what the children call it these days, right? Hashtag. Except it's really just a number sign. All right. What about the jump discontinuity? Is the function defined at C?
Yes.
Okay. Does the limit as x approaches C exist?
No.
No. So this one fails number 2. And which one does the infinite discontinuity fail? Fails number
1.
1. The function is not defined at x equals C. Okay. So just know those different types of discontinuities. How do we get the removable discontinuities? These come from 0 over 0. Right. What about the jump discontinuities? These will normally come from like a piecewise function or something. And what about the infinite discontinuities? Those show up when you have a constant divided by 0. So you should sort of have a general idea of when those appear also. Good or no?
Yes.
All right. All right, that's good enough for today. We'll stop there. We only have about 5 minutes left, so sounds good. Any questions on what we did today?